Hello, I'm gonna try this video. There's the second video I'm trying. I'm not sure if it's gonna be good. I didn't like the last video. I think the quality could be better, and I did some tweaks, so it gets better. This microphone from my sister, so I'm not sure if it's work, but I hope it works. And let's go. Now I'm studying these memory systems. I am doing these blog posts, right? I think this setup will be good for now. I think it's a good way so I can interact with the camera and show what I'm doing without like recording the screen and putting the image small here, because the main goal of this is like improve my communication skills and actually my proficiency in presenting things. So let's go. I did this memo post is not ended yet. It's like I think it still have a lot to do, but let's go. That is latch and flip flops as like simple at logic gates level for ways of storing memory. We are going to use mainly the D flip flop that goes to the cache RAM. Cache memory that exists is SRAM for L1, L2, L3 system in CPUs. There are these registers too. I didn't go too deep in the register because I think I want to talk more about that when I talk about SING. That's like this one, single instruction, multiple data, that is really, really cool, mainly for database. So I think this one will be good, right? So let's go through the one I want to talk about now. This is a SRAM that is static to handle memory access. That is like a simple six transistor system for storing 1 bit that you can see in this schema that is simplified just for learning purpose. Yes, not simplified, just drawingly simplified. So let's go. Here we have two transistor that is show the word line to BLs. That's like bit line. Here we are gonna actually store the data. So one will be one, other will be zero, and the difference between those will be the actual result. For example, the bit line have one, and the bit line cap that is have this line above. So 1 and 0, the difference is high. That would be block line is high, and block line with the line is not high, that's low. So this one would be 1. Otherwise, if the block line is 0 and block line with the cap is 1, this will be 0. And why am I saying that? Because mostly, for me actually, I didn't know it was like that, but it's using a differential sense amplifier that compare these two lines and actually find the value that is stored in this bit system based on that. So here we have two NOT gates. So if this side is 1, this other side will be 0, because 1 goes here, get this logic gate NOT, and this will be 0, and NOT again, this will be 1. So we can just store like the inversely the data represents there. And here we have the word line that is, you can imagine this system have a lot of this one in multiple lines and multiple layers and things. And when this word line is activated, this specific bit system, like this SRAM will be working. This is offline, this SRAM will just be storing the data, but it's not accessible or not writable, not readable and not writable. So just store without the word line. When the word line is active, the chains in there you can write and actually read. I have this other blog post that I was reading. This guy is like really cool, and I actually learned really much about using his blog post. And it represents like each of these intersections is like one SRAM. So I have a lot, and horizontally is the word line and vertically is the bit line. Of course, the bit line had two, but is represented with one just to simplify. So going back to the memory, this is how it works. At the smaller level, there is the representation of all the transistors and the bit line is here, the other bit line is here, the BLB. This here is the word line. It's not going forward, but I mean it's a line that continues going, but for simplification, it's just here. Here we have key B and key, which would be in your case, it's not represented here, but key B and P is also here. Uh, okay, this block is a CMOS inverter. Yes, CMOS inverter. You can just see it here. It's basically the NOT gate we were talking about. So you, it's basically if this the input is high, this side will just close. So the actual energy source will not flow to the output, which will be the high voltage, and will just flow from here. So it will be a low voltage and it will be zero. And if otherwise, if this is not coming, if the energy is not coming from the inputs, like it's not high, it's not one, this VDD will go directly to the output, so it will be a high energy, and we get the one, like the activation. So getting back, have two of these. You can imagine that this is like the not gates like that, but is flattened to the horizontal and works basically the same. I'm to understand that to do the blog post and make it more simplified. So I'm not sure if for now it makes sense, but it's just a way to start a bit, and you have multiple one side to side and layers and actually horizontally and vertical layers. So I'm still writing about that. I'm not sure if it's gonna be actually good this case because I'm a bit confused too. It's still not that proficient, but I think writing about will make me proficient in the sometime. So that's all.